Question 1. Firstly, could you please briefly introduce yourself and the main research work of your research group?
So my name is Elie Paillard. So I'm French. I did engineering study in France, then a PhD thesis also in France, in Grenoble, on polymer electrolyte for lithium metal batteries. So I started in 2004 on the topic in the labs where they have been proposed originally by Professor Michel Armand. Then I moved to United States for 2 years for a postdoc, where I started working on ionic liquid based electrolyte for supercapacitor and lithium batteries. Then I moved back to Europe, where I got a position in Germany, first at the MIT Institute, then at the Helmholtz Institute, Ulm, and then at the Helmholtz Institute Münster, as the battery research was really taking off in Germany, where I was tackling a whole range of topics, from nanostructure anodes to binder to electrolyte studies. And finally, I got my own group in Germany. And in 2020, I got this associate professor position in Politecnico di Milano, which is one of the best universities in Europe. So I took the opportunity to come here. And currently, the group is starting being built, since the funding situation is not as good in Italy as in Germany. But my main topic of studies are lithium metal batteries, and especially the interface between the lithium metal and the electrolyte itself. So I work on lithium metal, but by extension also on other technology, such as lithium ion, which is much more applied than lithium metal. So I do at the same time apply studies for within European project where the technology readiness level is a bit higher, and at the same time more innovative studies for next generation batteries with a focus on the anodes, the electrolyte, and the interface in between. So I work on polymer electrolytes. The main reason being that lithium-ion battery reach their limits in terms of energy density. So the idea is to switch from a graphite-based anodes to lithium metal anodes. And in this case, the cycling is quite challenging. And also the safety issues are becoming more and more important. So it's quite important to have electrolytes that are not as flammable and that can act as a real separator between the anode and the cathodes to enable the lithium metal electrodes. So on this regard, I'm trying to tackle all the reasons that leads to the dendrite growth, and there are many, many. So I don't know if I should do a scientific presentation here, but the reasons are both the transport limitation in the electrolyte, but also even at low current rate, we have issues. So the confinement of the lithium metal electrode is very important. So that's the reason why I'm working in what I'm working today.
Question 2. As the newly appointed Associate Editor of Energy Materials, what are your expectations for this journal? What criteria will be used in selecting manuscripts?
So my expectation is that Energy Materials will become one of the reference journal for energy materials. Since there are already quite a bit of journal in the area, it's very important to have very high quality research presented in the journal. So the idea is not to have special criteria for selection. They are always the same. The research should be sound. The experiments should be well presented and appropriate versus what you want to show in your study. So what I pay attention to is, at the same time, the experiment should be sound and well presented and the data well analyzed, although this is also for the reviewer then to judge. But also I check that the results are innovative enough, because there are so many publications now in the field that it's quite difficult to make a difference in terms of impact if the results are not innovative. So this is a main criteria. But at the same time, if you want to have a very innovative results, you have to pay attention that the claims are not overinflated, because we have an issue in general in the battery field, which is my field, but in general, I suppose in the energy field, because there is so much research and activities that the group tend to inflate a little bit the results. And it's a concern, especially for policymakers. For instance, in Europe, there are big working group trying to make roadmaps and trying to orient the funding of the European Union. And we found out that it's an issue to compare results from one article to another, because the results are always obtained in a way to present best for showing the best result possible to the journal. But then it becomes sometimes a little bit difficult to compare the results from one article to another, because the conditions are completely different. So for me, it's quite important to have all the experimental conditions very well stated, because we are not working on a field where we have a material, we analyze it, we need to build a device, and since from the materials to the device, there are several steps in a row, it can be quite difficult to, to reproduce the results for someone who is not in the field, because there is already quite a bit of technology involved just to manage to reach the results and have cells that can work well. So this is one of the criteria I pay strong attention to, is that the experimental conditions are well stated, and then that are properly analyzed, and then from this data that the claims are not overinflated, because many people that are not really in the field read now the articles, especially the policymakers, to try to orient the research and development fundings, at least at the EU level, but I suppose it's the same as in the United States or China or Japan or any countries. So it's important to have data that can be compared with one another, and the best way of doing that is to ensure that the experimental conditions are very well explained in the manuscript. Then the criteria, they are the same for all journal. Since we want to have a high quality journal, we want to be more strict with this criteria than maybe journals that do not aim at having such a high impact as energy materials.
Question 3. You previously served as a guest editor for the special issue Electrolytes and Interlayers for Next Generation Batteries in the Energy Materials Journal. Can you introduce the importance of electrolytes and interlayers in batteries?
Yes, so the electrolyte is very important from several points of views. First of all, it has a function in the batteries in general, is to transport ions from one side to the other, especially for lithium-ion battery or lithium metal batteries, where the electrolyte is there to insulate electrochemically the electrodes together with the separator and allow the ionic conduction. So this is quite simple, and one might think that the highest conductivity would be the best, but the problem is, since in advanced battery technology such as lithium metal batteries or even sodium ion batteries, lithium ion batteries, we use anodes that operates at a potential that is much below the thermodynamic stability of the electrolyte itself. It's very important then that the electrolyte reacts with the anodes to form a layer that is protective. So this is the case for all lithium metal and all lithium ion batteries. So on the one hand, you need to have an electrolyte that is able to form this layer in the best way possible. And on the other hand, the electrolyte's function is to transport lithium as fast as possible. So the issue is these two characteristics of the electrolyte often do not match. This is where the interlayer idea comes from, is to have a layer that have different characteristics compared to the electrolyte. For instance, higher mechanical property or lower mechanical property. because there are different cases possible. For instance, if you have a very soft electrolyte, the mechanical property of the electrolyte are not enough. Let's take the example of lithium metal. Lithium metal is relatively soft, but if you have strong mechanical property and you apply pressure, it's possible to confine it and prevent it to grow, at least at low current rate. And in this case, we want to have a mechanical barrier. So if we use all solid-state electrolytes, such as ceramic or glass electrolyte, they have quite strong mechanical property, and they can confine the lithium. But then they are very rigid. In this case, the idea is to have an interlayer that would be softer to keep the contact with the anode, because the volume change are quite important with these metallic anodes. So in this case, we need to have a very good contact. On the other hand, if we go for polymer electrolyte, which is more my topic, if we want to have high conductivity, very often the mechanical property of the polymer decrease significantly. And in this case, we might want to add an interlayer that have stronger mechanical property than the polymer electrolyte. So this is a field of research that is very open right now because there is intense research for this solid-state battery and next-generation battery, although it seems quite obvious that first quasi-solid-state battery will come out. And what are quasi-solid-state battery? For instance, they combine solid electrolyte with a liquid electrolyte or a polymer electrolyte that act as an interlayer because it's quite difficult to have an electrolyte that is at the same time very conductive, at the same time has a very good interfacial reactivity with the anodes, and is stable in oxidation to operate the cathodes. Since solid state allows that, it's possible to layer the different electrolyte. So each layer of the electrolyte has different properties, but at the same time, we increase the number of interfaces and the number of issues that can arise in interfaces. That would be the part of polymer electrolyte and interlayer that deal with the mechanical confinement. Now, dendrite, they don't only grow because you don't have enough confinement, because you have two extreme cases of dendrite, which is basically the deposition of lithium, not in a flat manner, but growing some dendrite. It's quite dangerous and it's quite damageable for the cycle life of batteries in general. So the idea is also to work on different approach to prevent the concentration gradients that occur in the electrolyte that can result in the full depletion of lithium when you try to plate lithium during the charge of the battery. So in this case, there are different approaches that can be done, and we can deal either at the interlayer level, at the interface between the lithium metal anode and the electrolyte, or at the electrolyte level. One of the approach typically is to use a single ion conductor where all the anions are fixed, which means that the lithium cannot form concentration gradients, because since we need to have charge neutrality, then normally the ionic concentration is fixed, at the exception maybe of the very close interface where we can have some effect there. In this case, we not interested in mechanical property necessarily, because we are trying to address the concentration gradients. And in the course of the development of the electrolyte, we might need to add some ingredients, let's say in the electrolyte, that make them rather soft to reach the level of conductivity we like, and then it can be necessary to add an interlayer. The other case I can think of is the interlayer. They form naturally, but they are usually quite small, and are considered as being themselves single ion conductor, because only the lithium should be able to go through and not the rest of the electrolyte, otherwise it would be reduced. So the idea is also interlayer can grow to the level of being a kind of electrolyte itself and have property. Either you have a bottom-up or a top-down approach. Either you can grow the electrolyte from the interlayer or grow the interlayer by putting the electrolyte in contact with the anodes. So there are many approaches that are being proposed right now in terms of electrolyte development and interlayer. So it's quite interesting because I personally don't know what is the best, if it's to have a hard electrolyte and a soft interlayer, a soft electrolyte and a harder interlayer. So all this field needs to be investigated. So that's why I propose this topic, because I think it can be very relevant for next generation batteries. And it's well in line with my research topic.
Question 4. What industries do you think will benefit most from the rapid development in the battery field, and which type of battery do you consider to have the most advantages?
So the first beneficiary of the development of new battery technology will be the battery company who commercialize these batteries. But then all the sector where they can be used, be it electronics or cars, now EVs are the main target for the development of lithium-ion batteries. But in Europe, for instance, there is a lot of research because of the ingress of the renewable energy and intermittent source of renewable energy, such as wind power or solar power. So there is a push for stationary storage and increase the capacity of stationary storage, either for grid stabilization or even for longer term. And different technology of battery could be used in this case. However, there is one category of battery which work quite well right now for different categories. It will be the lithium-ion battery, and especially the graphite lithium iron phosphate technology. Why? Because it's not the most energy dense technology compared to high nickel batteries. However, the cycle life is very good. The energy density is sufficient, in my opinion, for powering electric cars. And last but not least, lithium iron phosphate is not a toxic material. So if it could be made a bit more dense in terms of volume, it will be really even better. But in my opinion, this is the technology that will occupy a growing share of batteries as electrification of EV develops. And we can see that many car manufacturers, from the Chinese BYD to Tesla or Volkswagen, are now using the lithium iron phosphate technology. It's also the technology that is used mainly for stationary energy storage because it's reliable, it's a bit more safe, because safety of batteries is linked on the one hand on the electrolyte that is flammable, but on the other hand, when things start going bad and we go into a thermal runaway, then the cathode can release oxygen. So this is especially true with the layered oxide and especially nickel-rich layered oxide, but it's not the case for phosphate. So lithium iron phosphate has this advantage that it will not release so much oxygen in terms of an accident, let's say, when the temperature of the battery increases. So in my opinion, it's a technology that will be spread very heavily in the next 5 years, together with nickel-rich lithium-ion batteries. Then in the upcoming technology, I think sodium-ion battery has its place, especially if the price of lithium increase as they are doing now, because although the technology readiness level is not as, I mean, there are commercial products, there are commercial batteries, sodium-ion batteries, but the performance is not as optimized as lithium-ion batteries. So I think there is still a little margin of progression for sodium-ion batteries. And since we have a big need for storage, I think for stationary energy storage, if the price of lithium goes up, I think the sodium-ion battery could be a good option. but I'm not ruling out other type of technology such as redox flow, etc. I think it's important to go in all directions at the same time to be able to select the most appropriate technology for a specific use at the end. But I would say lithium-ion battery and graphite LFP, since there are need for larger and larger energy storage, the energy density is not the main point. It's more the cost and the lifetime, because it's the cost per cycle that is important for stationary energy storage. So in this case, I believe in graphite LFP, lithium iron phosphate, and sodium-ion battery. But I'm not so sure in the term of sodium-ion battery which technology will dominate, if it will be the Prussian white cathodes or just the layered oxide that are a bit easier to implement for production, from my understanding.
Question 5. How do you balance your research work and life?
Yes. So my case is a bit special because I mixed the life and the work quite well, since I married a researcher on lithium-ion battery. So she's a professor also at Politecnico di Milano and moved together with me. She's more a specialist of cathodes, and she's editor of another journal also on batteries. So we are really lithium or battery couple. So it's quite convenient sometimes and quite annoying at other time, because since we work in the same laboratory, if we have some issues with kids, for instance, we can one can take over the other one in the lab or for the kids. So it's quite convenient in our case, although having the two parents professor and involved in research and project and working group. Sometimes it's a little bit difficult, but we manage.